In the darkness of space, far beyond the orbit of Neptune, something extraordinary spins in the frozen reaches of our solar system. It defies everything we thought we knew about planets and dwarf planets. It shouldn't exist, yet it does. This is the story of Haumea, the most unusual planet in the universe, a world so bizarre that when astronomers first discovered it, they thought their instruments had malfunctioned. The year was 2004, and two teams of astronomers were locked in a bitter race that would soon erupt into one of the most contentious disputes in modern astronomy. On one side was a team led by José Luis Ortiz at the Sierra Nevada Observatory in Spain. On the other was Michael Brown and his colleagues at the California Institute of Technology, working with data from the Palomar Observatory. Both teams were scouring the outer solar system, searching for new worlds in the vast frontier beyond Neptune. What neither team knew was that they were both tracking the same object, an ice world that would rewrite the rules of planetary science. The Spanish team announced their discovery first, on July 29, 2005, reporting the detection of a new object they had been tracking since images taken in March 2003. But just days later, Michael Brown's team claimed they had actually discovered the object first, having identified it in images dating back to December 2004. Brown argued that the Spanish team had only found the object after accessing his team's observation logs online, essentially using his data to locate the object in their own older images. The accusation sparked immediate controversy. Had the Spanish team legitimately discovered the object independently? Or had they gained an unfair advantage by viewing Brown's observation plans? The debate grew heated, with accusations and counter-accusations flying between the two groups. International astronomical organizations had to step in to examine the sequence of events. Eventually, credit was officially given to Brown's team for the discovery, though the controversy left a bitter taste in the astronomical community and raised important questions about data sharing and discovery protocols in the digital age. But the drama of discovery was nothing compared to the astonishing nature of what had been found. As more observations poured in and astronomers began to analyze the light reflecting off this distant world, they realized they were looking at something unprecedented. This wasn't just another icy rock tumbling through the darkness. This was something that challenged fundamental assumptions about how celestial bodies behave. To understand Haumea, we must first understand its neighborhood, a realm of space so remote and mysterious that we're only beginning to grasp its true nature. Haumea resides in the Kuiper Belt, a vast donut-shaped region of space extending from about 30 astronomical units from the Sun, just beyond Neptune's orbit, to approximately 50 astronomical units outward. An astronomical unit, for context, is the distance from Earth to the Sun, roughly 150 million kilometers. This means Haumea orbits at an average distance of about 43 astronomical units, or more than 6 billion kilometers from the Sun. At this distance, the Sun appears as nothing more than an especially bright star, providing precious little warmth or light. The Kuiper Belt is a cosmic graveyard and museum combined, a repository of ancient materials left over from the formation of our solar system 4.6 billion years ago. When the planets were forming closer to the Sun, incorporating most of the available material in the inner solar system, the outer regions remained populated by countless icy bodies that never coalesced into planets. These frozen remnants hold clues to the conditions and composition of the primordial solar nebula, the cloud of gas and dust from which everything in our solar system formed. Scientists estimate that the Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across, and trillions of smaller bodies, all orbiting in the perpetual twilight of the outer solar system. Haumea shares this realm with other famous residents, including Pluto, the world that sparked its own controversy when it was reclassified from planet to dwarf planet in 2006, just as Haumea was being discovered. The neighborhood also includes Eris, Makemake, and countless other icy worlds, some large enough to be round, others irregular chunks of rock and ice tumbling through the void. But even among these strange and distant objects, Haumea stands out as uniquely peculiar. Understanding exactly how peculiar requires us to examine what astronomers observed as they studied this newly discovered world. When light reflects off a celestial body, it carries information about that object's size, shape, surface composition, and rotation. As astronomers measured the light curve of Haumea, tracking how its brightness changed over time, they encountered readings that seemed impossible. The object's brightness was varying in a way that suggested it wasn't spherical, like virtually every other large object ever observed in space. Instead, the light curves indicated an elongated shape, something stretched out like a football or rugby ball. At first, astronomers suspected a mistake. Throughout history, planets, moons, and large dwarf planets observed in our solar system had all proven to be essentially spherical. This isn't coincidental, but rather a consequence of gravity. When an object in space grows large enough, its own gravity becomes strong enough to pull it into a sphere, the shape that minimizes gravitational potential energy. For rocky bodies, this typically occurs at diameters above about 600 kilometers, while icy bodies, being less rigid, achieve roundness at even smaller sizes. The assumption that large objects must be round is so fundamental that when measurements suggested otherwise, the natural response was to check the instruments and recalculate. But as more observations accumulated from multiple telescopes and different teams of researchers, the conclusion became inescapable. Haumea truly was elongated, stretched into an ellipsoidal shape unlike anything previously seen in a body this large. The measurements indicated that, rather than being a sphere, Haumea was pulled out into an egg-like form, longer than it was wide, defying the expectations built up over centuries of astronomical observation. The scientific community had to confront an uncomfortable reality. Their instruments weren't malfunctioning. The universe had presented them with something entirely outside their experience, a world that broke the rules they thought governed planetary formation. The question immediately arose as to what could cause such a bizarre shape. The answer lay in another extraordinary characteristic of this distant world, something that became apparent as astronomers tracked the periodic variations in its brightness. Haumea was spinning, and not just spinning, but whirling at an absolutely incredible rate. As Haumea rotates, different portions of its elongated shape present different amounts of surface area to observers on Earth, causing its brightness to vary. By timing these variations, astronomers could determine how long it takes for Haumea to complete one full rotation. The result was shocking. Haumea completes a full rotation in approximately 3.9 hours. To put this in perspective, Earth takes 24 hours to rotate once, giving us our familiar day and night cycle. Mars rotates in about 24.5 hours, similar to Earth. Jupiter, the fastest spinning planet in our solar system, completes a rotation in just under 10 hours, despite being the largest planet. But Haumea, despite being large enough to qualify as a dwarf planet, spins nearly 3 times faster than Jupiter. This makes Haumea one of the fastest rotating large objects known in the solar system. Only some small asteroids spin faster, and they're tiny rocks, not world-class objects measuring hundreds or thousands of kilometers across. For something of Haumea's size and mass to be spinning this rapidly is extraordinary and immediately suggested that something dramatic must have happened to set it rotating so fast. Celestial objects don't naturally spin this quickly. Planets and dwarf planets form through the gradual accumulation of smaller bodies, a process that typically results in relatively slow rotation rates. For Haumea to be spinning as fast as it does, some tremendous force must have given it a violent push, imparting enormous rotational energy. The extreme spin rate isn't just a curiosity, but the key to understanding Haumea's bizarre shape. The two characteristics are intimately connected through the physics of rotation and the balance between gravitational and centrifugal forces. To understand this connection, imagine yourself on a playground, roundabout, or merry-go-round. As it spins faster and faster, you feel yourself being pulled outward, away from the center. This sensation is caused by what we call centrifugal force. Though technically, it's not a true force, but rather the result of inertia, your body's tendency to move in a straight line while the rotating platform continuously changes your direction. The same principle applies to Haumea, but on a cosmic scale. As the dwarf planet spins rapidly, every particle of ice and rock on its surface and within its interior experiences this outward pull. At the equator, where the rotational velocity is highest, the outward centrifugal acceleration works against gravity, effectively reducing the net gravitational pull. At the poles, which are on the rotation axis and therefore not moving in a circle, there's no centrifugal effect, and gravity acts at full strength. This differential creates a tug-of-war within the dwarf planet's structure. The equatorial regions are pulled outward while the polar regions are compressed inward, resulting in an oblate or flattened shape. For most planets and moons in our solar system, this effect is relatively subtle. Earth itself is slightly flattened at the poles and bulges at the equator due to its rotation, but the difference is small, with the equatorial diameter only about 43 kilometers larger than the polar diameter out of Earth's total diameter of nearly 13,000 kilometers. We perceive Earth as essentially spherical because the distortion is less than 1%. But for Haumea, spinning so incredibly fast, the effect is far more dramatic. The centrifugal force is so strong that it overwhelms the tendency of gravity to pull the object into a sphere, stretching the dwarf planet into an elongated ellipsoid. The physics involves a delicate balance. Haumea isn't rigid like a steel ball, but rather has some plasticity, particularly in its deeper layers where pressure and temperature are higher. Over time, the rapidly spinning world has deformed itself to reach an equilibrium shape where the combined effects of gravity and centrifugal force are balanced. Material has effectively flowed from the poles toward the equator, piling up in a bulge that extends the equatorial diameter dramatically while leaving the poles relatively flattened. The result is the stretched out shape that initially seemed so impossible to astronomers. Theoretical models and observations have combined to give us estimates of Haumea's actual dimensions, and they're truly extraordinary. The longest axis, running through the equator, measures approximately 2,300 kilometers from one side to the other. The intermediate axis, also in the equatorial plane, but perpendicular to the longest axis, spans roughly 1,700 kilometers. The shortest axis, running from pole to pole, is only about 1,000 kilometers. In other words, Haumea is more than twice as long as it is tall, like an egg or football stretched even further than normal proportions would suggest. To help visualize these dimensions, consider that the distance from New York City to Miami is about 2,000 kilometers. If you could somehow place Haumea next to Earth and align its longest axis horizontally, it would stretch from New York to Miami. Yet from pole to pole, it would only span a distance equivalent to traveling from New York to the southern tip of Florida. This isn't a subtle distortion, but an extreme deformation that gives Haumea a shape unlike any other world its size. If you could see Haumea from space, it wouldn't look like the familiar spherical planets and moons we're used to. Instead, you'd see something that looks almost artificial, as if someone had grabbed a spherical world and stretched it like taffy. The natural question becomes, what could have caused Haumea to spin so fast in the first place? Dwarf planets don't naturally form with such extreme rotation rates. The answer almost certainly lies in a cataclysmic event that occurred billions of years ago in the outer solar system. A collision so violent that it fundamentally altered Haumea's nature and created the bizarre world we observe today. The leading theory suggests that early in the solar system's history, when the Kuiper Belt was far more crowded than it is today, Haumea was struck by another large object in a grazing. High-speed impact. Unlike a head-on collision that might have shattered both objects into countless fragments, this glancing blow delivered an enormous amount of rotational energy, while leaving Haumea largely intact. Imagine two cars sideswiping each other, one clipping the rear quarter panel of the other. The struck car doesn't just move sideways but begins to spin. The same principle applies to celestial impacts, but with energy scales that dwarf anything in human experience. Computer simulations of such collisions suggest that the impactor might have been perhaps half the size of Haumea itself, a substantial world in its own right, measuring hundreds of kilometers across. As it struck Haumea at speeds of several kilometers per second, the kinetic energy of the impact was converted into rotational energy, setting Haumea spinning like a top. The collision would have been catastrophic beyond imagination, releasing energy equivalent to trillions of nuclear weapons, vaporizing portions of both objects, and sending debris fountaining into space. The heat generated would have been sufficient to melt and even vaporize ice and rock, creating a brief inferno in the frozen outer solar system. Yet, Haumea's core survived, now spinning at a furious rate that has persisted for billions of years. The violence of such an impact also helps explain another peculiar feature of Haumea, its unusual surface composition. Unlike many Kuiper Belt objects that have dark, reddish surfaces coated with organic compounds formed by billions of years of radiation exposure, Haumea is remarkably bright, reflecting about 70% of the sunlight that reaches it. This high reflectivity, or albedo, is characteristic of clean crystalline water ice, suggesting that Haumea's surface is covered in relatively pure ice without the darkening contaminants found on many similar objects. The collision theory provides a natural explanation for this pristine surface. The impact would have stripped away Haumea's outer layers, exposing fresh ice from the interior. This ice, buried and protected since Haumea's formation, would not have been darkened by eons of radiation exposure. Additionally, the heat from the impact might have caused surface ice to sublimate and then refreeze, creating a fresh coating of crystalline ice. The result is that Haumea shines brightly in the darkness of the Kuiper Belt, one of the most reflective objects in the outer solar system, its surface a testament to the violent event that reshaped it billions of years ago. The presence of crystalline water ice is itself interesting because it tells us about the conditions on Haumea's surface. Water ice can exist in different crystalline structures depending on temperature and pressure. The crystalline form observed on Haumea requires relatively warmer temperatures, at least compared to the frigid normal of the Kuiper Belt, to form and remain stable. This might seem contradictory given Haumea's enormous distance from the Sun. But even in the outer solar system, processes exist that can generate or preserve crystalline ice. These might include recent cryovolcanism, where ice erupts from the interior carrying heat, or ongoing sublimation and refreezing cycles, or simply the preservation of ice that crystallized during the heat of that ancient impact. Yet Haumea's surface isn't entirely uniform. Observations have revealed a peculiar feature that adds another layer of mystery to this already bizarre world. Against the bright, icy background of Haumea's surface, astronomers have detected a dark reddish spot. This region appears substantially less reflective than the surrounding terrain and exhibits a distinct coloration that stands out in spectroscopic observations. The spot seems to be stable and rotates with the dwarf planet, indicating it's a genuine surface feature rather than a temporary phenomenon. The presence of this red spot raises intriguing questions about Haumea's surface processes and history. Several theories attempt to explain what might cause this distinctive coloration. One possibility involves organic compounds, complex carbon-based molecules that can form when simpler ices like methane and nitrogen are bombarded by solar radiation and cosmic rays over geological timescales. These organic compounds, called tholins, are reddish or brownish and have been detected on many objects in the outer solar system. Perhaps the red spot is a region where some ancient material from before the Great Collision has survived, or where different surface processes have allowed organic compounds to accumulate. Another theory suggests the red spot might be material from a more recent, smaller impact, debris from a collision with another Kuiper Belt object that splashed different material onto Haumea's surface. If the impactor had a composition different from Haumea's pure ice, perhaps containing more rock or organic compounds, it could have created a discolored patch. Alternatively, the spot might represent a region where subsurface material has been exposed, perhaps by the fracturing of ice or localized sublimation, revealing a different composition beneath the pristine surface layer. Some researchers have also speculated about the possibility of cryovolcanism, the eruption of liquid or vaporized ices from beneath the surface. On icy worlds, water mixed with substances like ammonia or methane can create a slushy mixture that behaves like molten rock does on Earth. If such material erupted onto Haumea's surface, it might create a region with different properties and coloration. However, for cryovolcanism to occur, Haumea would need some source of internal heat, which is questionable given its size and age. The collision that set it spinning might have generated enough heat to drive some geological activity, but whether such activity could persist to the present day remains uncertain. The truth is that without closer observation, perhaps from a spacecraft visiting Haumea, we cannot definitively explain the red spot. It remains one of many mysteries surrounding this enigmatic world, a reminder of how much we still have to learn about the distant regions of our solar system. The collision that shaped Haumea had consequences extending far beyond the dwarf planet itself. The tremendous impact didn't just set Haumea spinning and strip away its outer layers, but also blasted enormous amounts of debris into space. Some of this material would have escaped Haumea's gravity entirely, becoming independent objects orbiting the Sun in the Kuiper Belt. Other fragments would have remained gravitationally bound to Haumea, forming a family of smaller objects sharing similar orbits. Astronomers have identified this collisional family, a group of Kuiper Belt objects that appear to be genetically related to Haumea, siblings born from the same violent event. The Haumea family consists of several known members, all sharing similar orbital characteristics and spectroscopic properties that suggest a common origin. Their orbits are similar in terms of semi-major axis, eccentricity, and inclination, clustering in a way that statistical analysis shows couldn't be coincidental. Moreover, Their surfaces show the same spectroscopic signatures of crystalline water ice that characterizes Haumea itself, lacking the organic rich reddish surfaces typical of most Kuiper Belt objects. This compositional similarity strongly suggests these objects were once part of Haumea, or the body that impacted it, blown off in the collision, and now orbiting independently as separate worlds. The existence of this collisional family provides powerful evidence supporting the impact theory for Haumea's rapid rotation and unusual shape. It's rare to identify such families in the Kuiper Belt because, unlike the asteroid belt, where collisional families are common and well studied, the Kuiper Belt's vast size and sparse population make it difficult to definitively connect related objects. The Haumea family is one of the few clear examples we have of a collisional family in the outer solar system, offering a unique window into the violent processes that have shaped these distant worlds. Among the debris from that ancient impact, some material remained close enough to Haumea to become captured as moons. Haumea has 2 known satellites, both discovered in the years following the dwarf planet's identification. The first and larger moon was discovered in 2005 by Michael Brown's team using images from the Keck Observatory. It was named Hi'iaka, after the Hawaiian goddess of dance and patroness of the Big Island, specifically the daughter of Haumea in Hawaiian mythology. Hi'iaka orbits Haumea at a distance of about 49,000 kilometers, completing one orbit approximately every 49 days. It's a substantial satellite, estimated to be about 300 to 400 kilometers in diameter, making it one of the larger moons in the outer solar system relative to its parent body. The second moon, Namaka, was discovered in 2006, also by Brown's team, in follow-up observations. Named after a water spirit in Hawaiian mythology, another daughter of Haumea, Namaka is smaller than Hi'iaka, measuring perhaps 100 to 200 kilometers across. It orbits much closer to Haumea, at a distance of only about 25,000 kilometers, completing an orbit every 35 days or so. Interestingly, Namaka's orbit is significantly eccentric and inclined relative to Hi'iaka's orbit, suggesting complex gravitational interactions between the moons and possibly indicating a chaotic past as the system evolved following its violent formation. Both moons almost certainly formed from the debris of the collision that set Haumea spinning. Rather than being captured, objects that formed elsewhere and later came under Haumea's gravitational influence, spectroscopic observations show that both moons share Haumea's unusual surface properties, particularly the dominance of crystalline water ice. This compositional similarity strongly suggests they're made of material that was once part of Haumea or the impactor, ejected in the collision and then reaccumulated into these satellite bodies. The moons are like children of that violent event, witnesses to the catastrophe that created the Haumea system we observe today. The orbital dynamics of Hi'iaka and Namaka provide astronomers with valuable information about Haumea itself. By observing the moon's orbits, applying Kepler's laws of planetary motion and Newtonian gravity, scientists can calculate Haumea's mass with considerable precision. These calculations reveal that Haumea has a mass of approximately 4 times 10 to the 21st kilograms, or about 28% of the mass of Pluto. Combined with estimates of Haumea's volume based on its unusual shape, this allows calculation of its density, which comes out to roughly 2 to 2.5 grams per cubic centimeter. This density is consistent with a composition dominated by water ice, with perhaps a rocky core, similar to many large Kuiper Belt objects, though the exact internal structure remains a subject of research and debate. Just when astronomers thought Haumea couldn't get any stranger, the dwarf planet had another surprise in store. On January 21st, 2017, Haumea passed directly in front of a distant star as seen from Earth, an event called a stellar occultation. This rare alignment offered a unique opportunity to study Haumea with unprecedented precision. As Haumea passed in front of the star, it would block the starlight, and by timing exactly when and where the starlight dimmed and reappeared, astronomers could precisely map Haumea's size, shape, and potentially detect features like an atmosphere. A dozen telescopes across Europe were coordinated to observe this event, positioned along the path where Haumea's shadow would sweep across Earth. As the occultation occurred, astronomers recorded the expected dimming as Haumea blocked the starlight. But then, something completely unexpected happened. The star dimmed briefly before and after the main occultation. Two subtle dips in brightness that indicated something else was blocking the starlight. Analysis of these additional dimmings revealed their cause. Haumea has a ring. This discovery was stunning for multiple reasons. Rings were known to exist around all 4 giant planets in our solar system, as well as around some asteroids. But Haumea became the first Kuiper Belt object and first dwarf planet known to possess a ring system. The ring's existence raised immediate questions. How could a small, distant world maintain a ring? What processes created it? And how has it remained stable over potentially millions or billions of years? The observations revealed key characteristics of Haumea's ring. It orbits approximately 2,287 kilometers from Haumea's center, which places it near what's called the 3-2 spinor, orbit resonance. This means that particles in the ring orbit Haumea 3 times for every 2 rotations of the rapidly spinning dwarf planet. The ring appears to be narrow, perhaps only 70 kilometers wide and relatively thin, likely no more than a few kilometers thick. It orbits in Haumea's equatorial plane, aligned with the dwarf planet's pronounced bulge. The ring's location and properties provide clues about its origin and nature. One theory suggests the ring is composed of material from a small moon that ventured too close to Haumea and was torn apart by tidal forces, the same gravitational stresses that create rings around planets. Another possibility is that the ring is debris from a more recent collision, perhaps between one of Haumea's moons and a smaller object, with the resulting fragments spreading out into a ring. Alternatively, the ring might be primordial material that was never incorporated into Haumea or its moons. Perhaps held in place by the complex gravitational environment created by Haumea's rapid rotation and unusual shape. The ring's long-term stability is puzzling. Theoretical calculations suggest that rings in this type of environment should be short-lived on astronomical timescales, with particles gradually spreading out or falling toward the parent body. Yet Haumea's ring appears well-defined and stable. Some researchers propose that one of Haumea's moons, perhaps acting as a shepherd satellite, helps confine the ring and prevent it from spreading, similar to how some of Saturn's small moons shepherd that planet's rings. However, Haumea's known moons don't seem to be positioned correctly for this role, suggesting there might be additional, yet undiscovered moonlets in the system. The discovery of the ring also refined our understanding of Haumea's shape and size. The occultation data allowed astronomers to create the most accurate profile of Haumea's outline, confirming the extreme elongation but providing more precise measurements than had been possible through light curve analysis alone. It painted a picture of a world even more bizarre than previously thought. A rapidly spinning ice egg surrounded by a delicate ring, accompanied by 2 moons, all hurtling through the darkness of the Kuiper Belt. The choice of name for this extraordinary world reflects both its unusual nature and its connection to its discoverer. When Michael Brown won the credit for Haumea's discovery, he earned the right to propose a name, following the International Astronomical Union's protocols for naming celestial bodies. Brown chose Haumea, the Hawaiian goddess of fertility and childbirth. This name was particularly fitting for several reasons. Haumea in Hawaiian mythology is associated with childbirth and fertility, themes that resonate with the dwarf planet's family of moons and associated objects, all born from the same violent event. The goddess Haumea is said to renew herself, being reborn through her various forms, which parallels how the dwarf planet Haumea was essentially reborn through its transformative collision. Additionally, Brown has a personal connection to Hawaii, where some of the key observations for discovering Kuiper Belt objects, including Haumea, were made using the Keck Observatory on Mauna Kea. The choice honored this connection while following the IAU's guideline that objects in the classical Kuiper Belt region should be named after creation. Deities from various mythologies. The moon's names, Hi'iaka and Namaka, continue this theme, being children of the goddess Haumea in Hawaiian mythology, just as the moons themselves are children of the dwarf planet, born from the same creative, destructive event. The naming scheme provides a poetic coherence to the system, linking mythology with physical reality, the creative power of the goddess mirrored in the creative violence of cosmic collision, the family relationships of myth reflected in the actual genetic relationship between Haumea, its moons, and its collisional family. It's a reminder that even in our scientific age, we still reach for stories and myths to help us understand and connect with the cosmos. For all that we've learned about Haumea, studying this distant world remains extraordinarily challenging. Located more than 6 billion kilometers from Earth, over 40 times more distant than the Sun, Haumea appears as nothing more than a faint point of light, even in the most powerful telescopes. The Hubble Space Telescope, capable of photographing galaxies billions of light years away, cannot resolve Haumea's unusual shape directly. Even the largest ground-based telescopes see it as just a dot, distinguished from background stars only by its slow motion against the stellar backdrop. Every piece of information we have about Haumea has been painstakingly extracted through indirect methods and ingenious techniques. The determination of its rotation period came from photometry, carefully measuring how its brightness varies as different portions of its elongated shape face Earth. The discovery of its moons required extremely sensitive detectors and sophisticated image processing to separate the faint dots of the satellites from the glare of Haumea itself. The spectroscopic analysis revealing its icy composition demanded collecting light from this dim object and spreading it into a spectrum, then identifying the subtle absorption features characteristic of water ice. The stellar occultation that revealed Haumea's ring was the product of meticulous planning. Such events are rare and fleeting. They require knowing Haumea's position with extreme precision, predicting exactly when and where on Earth its shadow will pass, and then coordinating multiple observatories in different locations to observe simultaneously in case clouds obscure the event at some sites. The entire occultation lasted only a few minutes, with the ring signatures appearing as dips in brightness lasting mere seconds. Yet from these brief moments of observation, astronomers extracted precise information about Haumea's size, shape, and ring system. Future observations face the same challenges. Haumea's orbit carries it through the ecliptic plane, and its distance from Earth varies, but it never comes close enough for easy observation. The James Webb Space Telescope, with its larger mirror and sensitivity to infrared light, might reveal new details about Haumea's surface composition and temperature distribution. But even this marvel of technology will see Haumea as essentially a point source. Detailed mapping of its surface, the kind of imaging that would reveal the nature of the mysterious red spot or show us the landscape of this spinning world, remains beyond our current capabilities using Earth-based or orbital telescopes. Imagining what it would be like to actually visit Haumea reveals just how alien this world truly is. Suppose you could stand on Haumea's surface, protected by some advanced spacesuit from the hostile environment. The first thing you'd notice is the gravity, or rather, the lack of it, combined with its bizarre variation across the surface. Haumea's relatively small mass means its surface gravity is weak to begin with, roughly 1/20th of Earth's gravity. But the rapid rotation creates even more unusual conditions. At the equator, where the rotational velocity is highest, the centrifugal effect would dramatically reduce the effective gravity. You'd weigh even less than Haumea's baseline low gravity would suggest, perhaps 1/30th of your Earth weight, or even less. A person weighing 70 kilograms on Earth might weigh only 2 to 3 kilograms at Haumea's equator, less than a house cat. You'd be able to jump enormous heights, and if you jumped too vigorously, you might actually achieve escape velocity and fling yourself into space, becoming a new moon of Haumea. Walking would be more like bounding, and you'd need to be tethered or use some form of propulsion to stay on the surface. If you could travel toward one of Haumea's poles, you'd notice the gravity gradually increasing as the centrifugal effect diminished. At the poles, sitting on the rotation axis where there's no circular motion, you'd experience the full force of Haumea's gravity, roughly double what you felt at the equator. This gradient would create a distinctly strange sensation, a noticeable slope seeming to pull you toward the poles, even though the actual surface might be relatively level. The difference in effective gravity between equator and poles would create unique dynamics for anything moving across Haumea's surface. Debris or ice particles would tend to drift toward the poles, roll toward them, creating a geographic sorting effect unlike anything on Earth. The landscape itself would be utterly alien. The surface is almost certainly heavily cratered, as Kuiper Belt objects are constantly, though infrequently, struck by smaller debris. But the craters would look different from those on more familiar worlds. The extremely low gravity means that ejecta from impacts would fly much farther, creating ray systems extending for hundreds of kilometers. The rapid rotation might also affect how crater ejecta is deposited, potentially creating asymmetric patterns as material ejected from an impact interacts with the spinning surface. The bright, icy surface would reflect whatever dim sunlight reaches Haumea, creating a landscape of brilliant whites, perhaps with the dark reddish patch visible as a distinct region. The sun itself would appear as merely a bright star, providing about 1/116th the light that Earth receives. This is far brighter than the full moon appears from Earth, but nowhere near daytime illumination levels. You'd see, by perpetual twilight, able to make out features and move around, but never experiencing true daylight. The stars would be visible even during the day, and with no atmosphere to scatter light or obscure the view, the sky would be filled with stars in all directions, the Milky Way a brilliant band arching overhead. Looking up, you might see Haumea's moons, Hi'iaka and Namaka, drifting across the sky over days. If the ring is dense enough and you're positioned at the right latitude, you might see it as a faint line arching across the sky, though from the surface it would likely be too faint and edge on to be prominent. The view would be haunting, beautiful in its strangeness. A frozen world spinning through space with a sky full of stars and no sound whatsoever, just the absolute silence of vacuum. the temperature would be hostile beyond imagination. Surface temperatures on Haumea hover around minus 240 degrees Celsius, or roughly 33 Kelvin. At this temperature, ice is harder than rock, behaving like granite or steel on Earth. Metals become brittle and shatter easily. Many materials that are gases or liquids on Earth are frozen solid. Nitrogen, oxygen, carbon dioxide all freeze at temperatures far higher than Haumea's surface. Even carbon dioxide, which we're used to seeing as dry ice at minus 78 degrees Celsius, would be far warmer than Haumea's environment. This extreme cold is a function of distance. The sun's energy drops off with the square of distance, meaning that at Haumea's distance of 43 astronomical units, the sun's heating effect is less than 1/1800th of what Earth receives. With no atmosphere to trap heat and no significant internal heat source, Haumea's surface simply radiates away whatever tiny amount of heat it receives from the distant sun, settling into equilibrium at this frigid temperature. The cold preserves everything, a natural deep freeze that has kept Haumea's surface relatively unchanged for billions of years, a frozen archive of ancient processes and materials. Yet even among the bizarre worlds in our solar system, Haumea's strangeness stands out. Our cosmic neighborhood contains many unusual objects. Saturn's moon Iapetus has a mysterious equatorial ridge and two-toned coloration. One hemisphere bright white, the other dark as coal. The asteroid Bennu resembles a spinning top, shaped by its rotation into a form with a pronounced equatorial bulge and a top knot of boulders at its poles. Hyperion, another moon of Saturn, is irregularly shaped and tumbles chaotically rather than rotating regularly. Miranda, a moon of Uranus, has a surface that looks like it was smashed apart and reassembled incorrectly, with wildly different terrains jumbled together. But Haumea combines multiple peculiarities into one package. Its extreme elongation exceeds that of any other world of comparable size. Its rotation rate surpasses nearly everything in its size class. It possesses a ring system, unexpected for such a small, distant object. It commands a family of related objects scattered through the Kuiper Belt, evidence of a violent past. Its surface is unusually bright and pure, covered in crystalline ice that hints at catastrophic resurfacing. All these characteristics emerge from a single event, the massive collision billions of years ago that transformed what was probably a fairly ordinary icy world into something extraordinary. What makes Haumea particularly scientifically valuable is precisely this uniqueness. By studying an extreme case, we learn about the limits of planetary processes and the range of outcomes possible from cosmic collisions. Haumea represents a natural experiment, showing us what happens when you spin a large ice ball fast enough to overcome gravity's tendency to create spheres. It demonstrates that ring systems can form and persist around small bodies far from the sun. It provides a clear example of a collisional family in the Kuiper Belt, helping us understand how common such violent events might have been in the early solar system. The question of whether humanity might ever send a spacecraft to Haumea is both tantalizing and sobering. The engineering challenges are immense, starting with the simple fact of distance. The fastest spacecraft we've built, New Horizons, which flew past Pluto in 2015, took 9.5 years to reach Pluto at about 39 astronomical units from the Sun. Haumea orbits farther out, and the mission would require even more time. We're talking about a journey of at least 15 to 20 years, possibly longer depending on the trajectory and whether we use planetary gravity assists to boost our speed. The energy requirements are daunting. Reaching the outer solar system requires enormous velocities to escape Earth's gravity and cross the vast distances involved. This means large rockets, substantial fuel supplies, or nuclear propulsion systems that are still largely conceptual. The spacecraft would need to be robust enough to function for decades in the harsh environment of space, with systems that can survive cosmic radiation, micrometeorite impacts, and the extreme cold of the outer solar system. Power is another challenge. At Haumea's distance, solar panels are nearly useless because the sun is too faint. The mission would likely require radioisotope thermoelectric generators, nuclear batteries that convert heat from radioactive decay into electricity, similar to what powered New Horizons and the Voyager spacecraft. Communication presents its own obstacles. At 6 billion kilometers, radio signals traveling at the speed of light take over 5 hours to reach Earth. This means no real-time control is possible. Commands sent from Earth won't arrive for 5 hours, and confirmation that the spacecraft received them won't come back for another 5 hours. The spacecraft must be largely autonomous, capable of making decisions on its own, especially during critical phases like a flyby, when events happen too quickly for ground control to intervene. But suppose we overcome these challenges and successfully send a spacecraft to Haumea. What might we discover? Close-up imaging would reveal the details of Haumea's surface for the first time. We'd see the actual landscape of this spinning world, the craters pocking its surface, the nature and extent of that mysterious red spot, possibly evidence of geological activity or lack thereof. We could map the surface in detail, creating topographic models that would reveal how the terrain has been shaped by the extreme rotation and low gravity. Spectroscopic instruments could analyze the surface composition with far greater precision than possible from Earth, identifying the exact forms of ice present, detecting trace compounds and organic molecules, mapping compositional variations across the surface. We might find regions where fresh ice has been exposed by recent impacts, or where sublimation has concentrated less volatile materials. The data would tell us about Haumea's formation, the composition of the primordial solar nebula in this region, and how billions of years of exposure to space have altered its surface. A spacecraft could study the ring in detail, measuring its density, particle size distribution, and exact dimensions. Cameras might capture images of the ring edge-on or backlit by the sun, revealing structure invisible from Earth. We could determine whether the ring is a single, coherent feature or composed of multiple narrow ringlets. Observations of how ring particles interact with Haumea's magnetic field, if one exists, would reveal information about both the ring and the dwarf planet's interior. The moons Hi'iaka and Namaka would become worlds in their own right rather than mere points of light. We'd see their surfaces, determine their shapes and sizes precisely, measure their masses through their gravitational effects on the spacecraft. If the mission included landers or impactors, we might even sample the surface material, confirming the composition indicated by spectroscopy and potentially measuring the age of the surface through crater counting. Perhaps most excitingly, a mission might discover things we haven't anticipated. Astronomy has a long history of surprises when spacecraft finally reach distant targets. Io's active volcanism, the geysers of Enceladus, the complex surface of Pluto, all were unexpected. Haumea might harbor its own surprises, features or phenomena we can't predict from distant observations. There might be additional moons too small or faint to detect from Earth. The ring might have gaps or braids or embedded moonlets. The surface might show evidence of processes we haven't considered. Yet, as exciting as such a mission would be, the reality is that no mission to Haumea is currently planned or funded. space agencies must prioritize among countless worthy targets with limited budgets. Missions to Mars, the outer planets, their moons, asteroids, and other objects compete for resources. Haumea, while scientifically fascinating, must compete with targets that might offer more immediate returns or address more pressing questions about life, planetary habitability, or threats to Earth from asteroid impacts. This doesn't mean a mission to Haumea will never happen. As technology advances, missions to the outer solar system become more feasible. New propulsion systems, more efficient power sources, and advances in autonomous spacecraft operation could reduce costs and mission duration. Perhaps in a few decades, when the current generation of outer solar system missions has returned their data and whet our appetite for more, Haumea will move up the priority list. Or perhaps a private venture, funded by philanthropists or space enthusiasts, will decide that solving the mysteries of this bizarre world is worth the investment. Until then, we continue learning about Haumea from afar, using every technological advance to squeeze more information from the faint light reflecting off its distant surface. Each new telescope, each refinement in observation technique, each clever use of rare events like occultations adds pieces to the puzzle. We're learning to study worlds we cannot visit, extracting their secrets through patience and ingenuity. The scientific value of Haumea extends far beyond mere curiosity about a weird object in the outer solar system. Haumea teaches us fundamental lessons about planetary science that apply throughout the universe. The physics governing Haumea's rotation and shape are universal. The same principles that affect objects everywhere from asteroids to galaxies. By studying how centrifugal force battles gravity to create Haumea's extreme elongation, we gain insights that help us understand other rapidly rotating bodies. Some neutron stars, for instance, spin even faster than Haumea, completing hundreds of rotations per second, and are similarly deformed into oblate shapes by their rotation. The collision that created Haumea and its family offers a window into impact dynamics at scales difficult to study elsewhere. Giant impacts have shaped planetary evolution throughout the solar system. The Moon likely formed from debris blasted off early Earth by a Mars-sized impactor. Mercury's large iron core relative to its size might result from a giant impact that stripped away much of its rocky mantle. The impact that created Haumea's family was smaller than these planet-forming collisions, but larger than the impacts that create typical craters. It represents an intermediate scale of collision, one that fundamentally alters an object without destroying it, and studying Haumea's family helps us understand this regime of impact physics. Haumea's ring system informs our understanding of how rings form and persist. Before spacecraft visited Saturn up close, we thought rings were primordial, left over from the planet's formation. Now we know that many rings are geologically young, continuously renewed by processes that grind down moons or capture debris from impacts. Haumea's ring, around such a small body, challenges our models and forces us to think more broadly about ring dynamics. If a dwarf planet smaller than Pluto can maintain a ring, what other objects might have rings we haven't detected? Might some of the thousands of Kuiper Belt objects possess their own faint ring systems? The Haumea collisional family provides rare evidence for the violent history of the Kuiper Belt. Early in the solar system's history, the outer regions were far more crowded, and collisions were common. Most of the debris from ancient impacts has since been scattered, ejected from the solar system, or accreted into larger bodies, erasing the evidence. But the Haumea family survived, its members still clustered in similar orbits, allowing us to identify them as siblings, billions of years after their violent birth. This proves that major collisions occurred in the Kuiper Belt and suggests that other families might exist, waiting to be discovered and teaching us about the collision rate and dynamics of the early outer solar system. Haumea also exemplifies the diversity of worlds in our solar system, reminding us that planets come in far more varieties than the 8 familiar worlds orbiting between Mercury and Neptune. The solar system contains hundreds of dwarf planets, thousands of large moons and asteroids, and millions of smaller bodies, each with its own characteristics and history. Some are volcanic, others dead and cratered. Some have atmospheres, others are airless. Some are rocky, others icy, and still others are mixtures of materials. Some are geologically active today. Others have been frozen in time for billions of years. Haumea, with its extreme spin and unusual shape, shows us that the range of possibilities is even broader than we might have imagined. This diversity isn't limited to our solar system. The thousands of exoplanets discovered orbiting other stars have revealed an even more astonishing variety of worlds. We've found hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, their atmospheres stripped away by stellar radiation. We've found super-Earths and mini-Neptunes, planet types that don't exist in our solar system. We've found planets orbiting binary stars, planets in highly eccentric orbits, planets that are probably covered in global oceans, and planets where it might rain molten glass sideways. Haumea reminds us that the universe is creative, constantly producing combinations of conditions and histories that lead to new and unexpected outcomes. Just as Haumea's particular history led to its unique characteristics, every world in the universe has its own story, its own combination of formation conditions, geological history, and external influences that make it what it is. No two worlds are exactly alike, and the more we explore, the more variety we find. From a philosophical perspective, Haumea challenges our tendency to categorize and define. We like to put things in boxes, to create clean categories that make the universe comprehensible. We define planets as having certain characteristics, moons as having others. But nature doesn't respect our categories. Haumea is a dwarf planet, but it's so elongated that it doesn't fit the typical picture of what a planet should look like. It has moons and a ring, features we associate with larger planets. It leads a family of smaller objects, like a planetary system in miniature. It's all these things at once, defying simple categorization. This is a recurring theme in astronomy and science more broadly. Nature is more complex and nuanced than our categories suggest. We find objects at the boundaries of our definitions, forcing us to refine our thinking. Pluto's reclassification from planet to dwarf planet was controversial precisely because it challenged how we think about and categorize solar system objects. Haumea, with its multiple unusual characteristics, continues this tradition of complicating our neat categories and forcing us to think more carefully about what we mean when we classify celestial bodies. There's also something deeply humbling about Haumea. Here is a world we didn't even know existed until 2004, despite having studied the solar system for centuries. It's not hidden in some impossible-to-observe location, but rather simply far away and faint, overlooked until technology advanced enough to detect it. The discovery reminds us how much remains unknown even in our cosmic backyard. If we only recently discovered a dwarf planet the size of Haumea, what else might be out there waiting to be found? Indeed, astronomers continue to search for additional large objects in the Kuiper Belt and beyond. Some scientists have proposed the existence of a Planet 9, a hypothetical world several times Earth's mass orbiting in the distant reaches of the solar system, based on clustering patterns in the orbits of extreme trans-Neptunian objects. Whether Planet 9 exists remains unproven, but the search continues, reminding us that the solar system may still hold major surprises. Haumea's discovery and subsequent study also highlight the importance of international cooperation in science. The observations that revealed Haumea's properties came from telescopes around the world: the Palomar Observatory in California, the Keck Observatory in Hawaii, the Sierra Nevada Observatory in Spain, and numerous other facilities. The stellar occultation that revealed its ring involved coordinated observations from 12 different locations across Europe. No single nation or institution could accomplish these observations alone. Science, particularly astronomy, has always been international, with researchers sharing data, collaborating on observations, and building on each other's work regardless of borders. This international character of astronomy offers a hopeful counterpoint to divisions. While nations may disagree on various issues, scientists continue to collaborate, united by curiosity about the universe. Discoveries like Haumea belong to humanity as a whole, not to any single country or institution. They expand our collective understanding, adding to the shared heritage of knowledge that we pass on to future generations. For future generations, Haumea represents a milestone in our expanding awareness of the solar system's diversity. Children born today are growing up in an era where dwarf planets, Kuiper Belt objects, and exoplanets are familiar concepts, whereas previous generations learned of 8 planets and little beyond them. The solar system of contemporary astronomy is vastly richer and more interesting than the one known to people living just a few decades ago. Haumea, with its bizarre characteristics, enriches this picture, giving young people a striking example of how strange and wonderful the cosmos can be. Educational programs and planetariums are beginning to incorporate Haumea and other recent discoveries into their presentations, though it hasn't yet achieved the recognition of Pluto or even some other dwarf planets like Eris. Perhaps in time, as we learn more about Haumea, and as the story of this spinning ice egg becomes more widely known, it will capture the public imagination more fully. It certainly deserves to be better known, as its story combines drama, mystery, and truly alien characteristics that make it one of the solar system's most remarkable objects. The name Haumea is gradually entering the astronomical lexicon, though it remains unfamiliar to many outside the field. Pronouncing it correctly as Haumea takes some practice for English speakers unfamiliar with Hawaiian pronunciation, but learning to say Haumea properly is a small gesture of respect for Hawaiian culture and for the choice its discoverer made in naming this world. Names matter in astronomy because they're how we remember and relate to distant objects that we can never directly experience. A good name should be memorable, meaningful, and appropriate to the object it designates, and Haumea succeeds on all counts. As we reflect on what Haumea means for our understanding of the cosmos, we're reminded that exploration never truly ends. Each discovery opens new questions. We now know Haumea exists, spins rapidly, has an unusual shape, possesses moons and a ring, and leads a collisional family. But we still don't know precisely how large the impactor was, the exact angle and velocity of the collision, or the internal structure of Haumea. We don't know why the red spot appears where it does, or whether Haumea has any geological activity. We don't fully understand how the ring remains stable, or whether there are additional small moons yet to be discovered. These open questions are not failures of science, but rather the nature of scientific progress. We answer one question only to find several more waiting beyond it. This is how knowledge advances, each generation building on what came before, gradually filling in details, occasionally overturning previous conclusions when new evidence demands it, always pushing toward a more complete and accurate understanding. Haumea stands as a testament to cosmic violence and beauty coexisting in a single object. The collision that created it was catastrophic, releasing energy beyond comprehension, shattering worlds and scattering debris across the Kuiper Belt. Yet, from that destruction came something remarkable, a spinning ice egg unlike anything else we've seen, accompanied by 2 moons and a delicate ring, all dancing together through the darkness, billions of kilometers from the sun. It's a reminder that violence and creation are not opposites, but rather different aspects of the same processes that shape the universe. In the grand scheme of the cosmos, Haumea is insignificant, a tiny ice ball in a remote corner of an average solar system, orbiting an unremarkable star in a typical galaxy. Yet to us, living on our own small world orbiting that same unremarkable star, Haumea is significant precisely because it exists, and because we've discovered it and begun to understand it. It represents our growing capacity to explore beyond our immediate environment, to learn about places we cannot visit, to piece together stories from fragments of light reaching our telescopes across billions of kilometers of space. The story of Haumea is ultimately a human story as much as a cosmic one. It's the story of astronomers competing to make discoveries and arguing over credit. It's the story of researchers collaborating across borders to observe a rare stellar occultation. It's the story of scientists piecing together evidence, proposing theories, testing hypotheses, and gradually building an understanding of a world they can barely see. It's the story of human curiosity driving us to explore, to question, to seek understanding, even when that understanding has no immediate practical application. Why do we care about Haumea? Not because it affects our daily lives, or because understanding it will solve any pressing problems facing humanity. We care because we're curious, because we want to understand the universe we inhabit, because there's joy and wonder in discovering that reality is stranger and more diverse than we imagined. We care because billions of years ago, 2 worlds collided in the outer reaches of our solar system, and the result was something unique and beautiful and bizarre, and we find meaning in knowing about it. Haumea orbits through the Kuiper Belt, endlessly spinning, making its rapid 3.9-hour rotation again and again and again, as it has for billions of years and will for billions more. Its moons slowly orbit, their paths traced by gravity and momentum. Its ring particles circle, each on its own trajectory, collectively creating a delicate halo around this spinning world. The collisional family members follow their independent paths through the Kuiper Belt, siblings scattered but still connected by their common origin. All of them are cold, distant, barely lit by a sun that appears as only a bright star in their sky. Yet from our vantage point, these cold and distant objects shine with significance. They tell us that the universe is full of wonders, that the familiar spherical planets of our childhood astronomy books represent only a fraction of the diversity that exists. They remind us that we live in a vast cosmos still largely unexplored, with discoveries waiting in every direction we choose to look. They teach us physics and planetary science while simultaneously showing us the limits of our current knowledge and technology. Haumea stands as perhaps the most unusual planet or dwarf planet in our solar system, a cosmic oddity that challenges our assumptions and expands our understanding. Its discovery story, dramatic and controversial, mirrors the high stakes of modern astronomy, where new discoveries can make careers and where credit matters. Its physical characteristics, from the extreme elongation to the rapid rotation to the ring system, make it one of the most bizarre objects we've yet encountered. Its collisional family and moons tell a story of ancient violence whose consequences persist billions of years later. Its bright, icy surface preserves evidence of that violent past while raising new questions about surface processes on distant, frozen worlds. As our technology improves and our knowledge expands, we'll continue learning about Haumea. Each new observation adds detail to our picture of this world. Each new theoretical calculation helps us understand the physics governing its behavior. Perhaps one day, decades or centuries from now, a spacecraft will make the long journey to Haumea and reveal its secrets in stunning detail. Until then, Haumea spins through the darkness of the Kuiper Belt, a cosmic enigma that reminds us that reality is always more interesting than fiction, that the universe continually surprises us, and that the quest for knowledge never ends, but rather opens new horizons with each discovery we make. In the outer reaches of our solar system, in the cold and darkness beyond Neptune, this elongated ice world spins and spins, a testament to the creativity of cosmic processes and the power of human curiosity to reach across billions of kilometers and understand worlds we may never touch. The implications of Haumea's existence extend into realms of planetary science that researchers are only beginning to fully appreciate. When we consider the formation of our solar system, we often think in terms of a relatively orderly process where dust and gas coalesced into larger and larger bodies, eventually forming the planets we see today. But Haumea's story reveals that chaos and violence played equally important roles in shaping the worlds we observe. The collision that created Haumea wasn't an isolated incident, but rather represents a type of event that must have occurred countless times throughout the solar system's history. During the first few 100 million years after the solar system's formation, the outer regions beyond Neptune were far more densely populated than they are today. Theoretical models suggest there may have been tens of times more mass in the Kuiper Belt region than exists there now. These countless icy bodies constantly interacted gravitationally, their orbits shifting and evolving as they tugged on each other. Collisions were inevitable and frequent. Some impacts were gentle, allowing bodies to merge and grow larger. Others were catastrophic, shattering objects into fragments that themselves became independent bodies orbiting the Sun. The event that created Haumea falls into this latter category, a collision energetic enough to impart tremendous rotational energy while still leaving a substantial, intact body. Computer simulations of such impacts reveal the incredible complexity of these events. When two large icy bodies collide at speeds of several kilometers per second, the impact doesn't simply create a crater as smaller impacts do. Instead, the kinetic energy is so enormous that it can partially or completely melt both objects, creating what's essentially a brief explosion of vaporized and liquefied ice and rock. Shockwaves propagate through both bodies at supersonic speeds, fracturing and heating the material they pass through. In the specific type of collision believed to have created Haumea, the impact was oblique rather than head-on. The impactor struck at an angle, delivering a glancing blow that transferred angular momentum efficiently. Think of it like a cue ball striking another ball at an angle in billiards. The glancing impact sets both balls spinning. In Haumea's case, the massive energy transfer set the larger body spinning at an incredible rate, while simultaneously blasting away a significant portion of its mass. The fragments that escaped became the members of the Haumea collisional family we observe today, Some fragments remained gravitationally bound and eventually coalesced into the moons Hi'iaka and Namaka. The main body, battered and spinning, gradually settled into the elongated equilibrium shape we observe, stretched by its own rotation into a cosmic football. The timescale of these events is worth contemplating. The actual collision would have been over in minutes or hours, a brief violent encounter in the vast emptiness of space. But the aftermath continued for much longer. The debris field would have taken days or weeks to disperse, with fragments flying outward at various velocities. Some pieces would have achieved escape velocity and departed the system entirely, becoming independent Kuiper Belt objects. Others, moving more slowly, remained in the vicinity. Over months and years, gravitational interactions would have caused some of these fragments to collide with each other or fall back onto Haumea. The ones that remained at sufficient distances gradually organized into stable orbits, becoming the moons we observe today. The reshaping of Haumea itself would have taken longer still. Immediately after the impact, the dwarf planet would have been spinning rapidly, but its shape wouldn't have instantly adjusted. Ice, even at these frigid temperatures, has some rigidity and can't instantly flow to a new configuration. But over thousands or millions of years, the constant stress from the centrifugal force would have caused the ice to deform plastically, slowly flowing from the poles toward the equator. This process, called viscous relaxation, allowed Haumea to eventually reach its current elongated equilibrium shape, where the stresses from rotation and gravity balance each other. Understanding this history helps us appreciate that Haumea isn't just an odd-shaped rock, but rather a fossil, a preserved record of one of the most violent events that occurred in the early Kuiper Belt. Every characteristic we observe, from its rapid spin to its elongated shape to its bright icy surface to its moons and ring, traces back to that single catastrophic encounter billions of years ago. Haumea is like a crime scene from the early solar system, and astronomers are the detectives piecing together what happened from the evidence left behind. This detective work extends to understanding the internal structure of Haumea, something we can only infer indirectly since we cannot see inside the dwarf planet. The density calculations based on Haumea's mass and volume suggest it's composed primarily of rock and ice, probably with a rocky core surrounded by a thick, icy mantle. But the exact proportions and structure remain uncertain. Some models suggest Haumea might have a relatively large rocky core, making up perhaps 2/3 of its mass, with ice making up the outer third. Other models propose different ratios. The uncertainty arises because we don't know Haumea's exact dimensions with perfect precision, and small errors in size measurements translate into larger uncertainties in volume and density calculations. The internal structure matters for understanding Haumea's evolution and current state. A larger rocky core would mean different mechanical properties, affecting how easily the dwarf planet could deform into its current shape. The distribution of mass between core and mantle also affects the moment of inertia, which influences rotation dynamics. Additionally, the core-mantle structure has implications for Haumea's thermal history. When the collision occurred, the tremendous energy release would have heated both the impactor and Haumea. The rocky core, being denser and having higher heat capacity, would have retained heat longer than the icy mantle. This internal heat might have driven some geological activity in the millions of years following the impact, potentially causing cryovolcanism or tectonic activity that reshaped the surface. Today, billions of years after the collision, any internal heat from that event has long since radiated away into space. Haumea is almost certainly geologically dead, frozen solid throughout. Without an internal heat source and lacking the tidal heating that keeps some moons geologically active, Haumea's interior is likely as cold and unchanging as its surface. The only processes modifying it now are external, impacts from smaller Kuiper Belt objects and cosmic radiation that slowly alters surface chemistry. Yet the ring system suggests that something relatively recent must have occurred. Theoretical calculations indicate that rings around small bodies like Haumea shouldn't be stable over billions of years. Perturbations from the moons, solar radiation pressure, and other effects should cause ring particles to either spiral inward and crash onto Haumea or drift outward and escape. The fact that Haumea has a ring implies either that it formed relatively recently, perhaps within the last few million or tens of millions of years, or that some mechanism continuously replenishes it. The recent formation hypothesis suggests that a small moon, either one we haven't detected or one that no longer exists, wandered too close to Haumea and was torn apart by tidal forces. This would have created a debris field that gradually spread out into the ring we observe. Alternatively, a collision between a small moonlet and a piece of Kuiper Belt debris could have shattered the moonlet, creating ring-forming fragments. In either scenario, the ring would be relatively young and would be expected to gradually disappear over the next several million years unless another moon-disrupting event occurs. The continuous replenishment hypothesis proposes that material is constantly being added to the ring, balancing the material being lost. Possible sources include micrometeorite impacts on Haumea's moons, which could splash debris into orbit, or sublimation of volatile ices from ring particles themselves, which could create pressure that counteracts the forces trying to clear the ring. However, calculations suggest these effects are probably too weak to maintain the ring indefinitely, making the recent formation hypothesis more plausible. The study of Haumea's ring contributes to our broader understanding of ring systems throughout the solar system and universe. Rings are more common than we once thought. All 4 giant planets in our solar system have rings, though Saturn's are by far the most spectacular. In recent years, we've discovered rings around asteroids, with the asteroid Chariklo possessing 2 distinct rings discovered through stellar occultation observations similar to those that revealed Haumea's ring. The dwarf planet Quaoar, another Kuiper Belt object, was recently found to have a ring as well. These discoveries suggest that rings might be a common feature of solar system objects across a wide range of sizes and locations. Each ring system teaches us something about the dynamics of orbiting particles, the interplay between gravitational forces and other physical effects, and the history of the parent body. Saturn's rings, though spectacular, are actually quite unusual in some ways, being extremely thin and showing complex structure created by gravitational interactions with Saturn's many moons. Jupiter's rings are dusty and faint, constantly replenished by impacts on small inner moons. Uranus and Neptune have dark, narrow rings that are poorly understood. Chariklo's rings orbit a tiny asteroid and shouldn't exist according to simple theories. Haumea's ring adds another data point, another example of how rings form and behave under different conditions. The diversity of ring systems mirrors the diversity of worlds themselves, each system unique, yet following the same fundamental physical laws. By studying many examples, astronomers can test their theories and develop more comprehensive models of ring dynamics. Questions about ring stability, particle interactions, the role of shepherd moons, and the effects of various forces can be addressed by comparing observations of different ring systems and seeing which theoretical predictions match reality. Returning to the question of exploration, we can imagine in more detail what a mission to Haumea might entail, and what technologies might make such a mission feasible in the coming decades. The primary challenge is propulsion, getting a spacecraft to Haumea in a reasonable time frame. Conventional chemical rockets, while powerful enough to launch spacecraft from Earth, are inefficient for sustained acceleration during interplanetary flight. The New Horizons mission to Pluto used a combination of a powerful launch rocket and a gravity assist from Jupiter to achieve the necessary velocity, but even so required nearly a decade to reach its target. For a Haumea mission, several advanced propulsion technologies could potentially reduce flight time and mission cost. Ion drives, which accelerate ions using electric fields powered by solar panels or nuclear generators, provide very low thrust but can operate continuously for years, eventually achieving high velocities. The Dawn mission successfully used ion propulsion to visit the asteroids Vesta and Ceres, demonstrating the technology's viability. A Haumea mission using ion propulsion might take 15 to 20 years, but could potentially carry more scientific instruments than a faster flyby mission using conventional propulsion. Nuclear propulsion, either nuclear electric or nuclear thermal, could provide more thrust than ion drives while being more efficient than chemical rockets. These systems use nuclear reactors to generate electricity or directly heat propellant, achieving higher exhaust velocities and thus better fuel efficiency. However, nuclear propulsion for space exploration remains largely untested, with technological and hurdles to overcome before it becomes operational. Another intriguing possibility is solar sailing, using enormous reflective sails to catch momentum from sunlight. While solar sails have been tested on small spacecraft and could theoretically achieve very high velocities, they work best close to the sun, where sunlight is intense. For a mission to the outer solar system, a solar sail would provide its greatest benefit early in the trajectory, accelerating the spacecraft as it departs the inner solar system before sunlight becomes too faint to provide significant thrust. Hybrid missions combining solar sail acceleration with other propulsion methods might offer advantages over conventional approaches. Regardless of propulsion method, a Haumea mission would require careful planning of its trajectory. Simply pointing the spacecraft at Haumea and accelerating wouldn't be optimal, because Haumea is constantly moving in its orbit. Mission planners would need to calculate a trajectory that intercepts Haumea at a future position along its orbit, taking into account the positions of planets that might provide gravity assists to boost the spacecraft's velocity or adjust its trajectory. These calculations are enormously complex, involving solving equations of motion for multiple bodies over decades-long timescales. The spacecraft itself would need to be designed for autonomy and reliability. At Haumea's distance, communication delays make real-time control impossible. The spacecraft must be able to make decisions independently, using onboard computers programmed with sophisticated algorithms that allow it to respond to unexpected situations. If a computer glitch or hardware failure occurs, the spacecraft needs redundant systems and the ability to switch to backup modes automatically. Everything must function reliably for 15 or 20 years or longer without maintenance, a daunting engineering challenge. Power supply presents another significant challenge. Solar panels are essentially useless at Haumea's distance because the sun provides less than 1/1/16th the light available at Earth's orbit. The spacecraft would almost certainly need to use radioisotope thermoelectric generators, devices that convert heat from radioactive decay into electricity. RTGs have powered many deep space missions, including the Voyager spacecraft still operating after more than 40 years and New Horizons. However, RTGs use plutonium-238, a material that's in short supply and expensive to produce. A Haumea mission would need to compete with other proposed missions for access to limited plutonium stockpiles. The scientific instruments carried by a Haumea mission would need to be chosen carefully to maximize scientific return while staying within mass and power budgets. At minimum, the spacecraft would carry high-resolution cameras to photograph Haumea, its moons, and its ring. Multiple cameras with different filters and wavelengths would allow color imaging and detection of compositional differences across the surface. A spectrometer would analyze sunlight reflected from Haumea's surface, identifying the specific minerals and ices present and mapping their distribution. This data would be crucial for understanding Haumea's composition and surface processes. Other instruments might include a magnetometer to detect any magnetic field Haumea might possess, which would provide information about its interior structure. A dust detector could measure particles in the ring and in the space surrounding Haumea, characterizing the size distribution and density of material. A radio science experiment could use precisely timed radio signals to measure Haumea's gravitational field with high accuracy, revealing information about mass distribution within the dwarf planet. If the spacecraft carried a small probe that could be released to impact Haumea's surface or one of its moons, the impact could create a plume of debris that the main spacecraft could analyze, revealing subsurface composition. The mission's most critical phase would be the flyby itself, assuming the mission follows a New Horizons-style trajectory rather than entering orbit. During a flyby, the spacecraft would pass through the Haumea system at high velocity, perhaps several kilometers per second relative to Haumea. The entire encounter would last only hours or days, with the closest approach lasting just minutes. During this brief window, all instruments would need to operate flawlessly, capturing as much data as possible before the spacecraft rushed past and Haumea receded into the distance once again. Every second of the flyby would be choreographed in advance, with the spacecraft executing a precisely planned sequence of observations. Cameras would capture images at predetermined times and orientations. Spectrometers would scan across Haumea's surface, following programmed patterns. The spacecraft's trajectory would be carefully designed to provide the best possible views of scientifically interesting targets, while also allowing observations of the moons, the ring, and different regions of Haumea's surface. If communication delays prevent real-time command, the spacecraft must execute this complex dance autonomously, adapting to any unexpected situations using its onboard programming. After the flyby, assuming the spacecraft survives the encounter undamaged, it would spend weeks or months transmitting its data back to Earth. At Haumea's distance, radio signals are extremely weak by the time they reach Earth, requiring enormous dish antennas and sensitive receivers to detect them. The data rate would be painfully slow, perhaps only a few thousand bits per second, or less. Transmitting gigabytes or terabytes of images and scientific data could take many months. Mission controllers would need to prioritize which data to transmit first, balancing the desire to see spectacular images quickly against the need to preserve scientifically valuable data in case something goes wrong. The cost of such a mission would be substantial, likely measured in hundreds of millions or even billions of dollars, depending on the mission architecture and instruments included. This cost must be weighed against other priorities and other missions competing for funding. Is a Haumea mission more valuable than another Mars rover, or a mission to Europa to search for life, or a large space telescope to study exoplanets? These are difficult questions with no objectively correct answers, involving value judgments about which scientific questions are most important and which discoveries would most benefit humanity. Despite these challenges, there are reasons to be optimistic about eventually exploring Haumea up close. Technology continues advancing, making missions to the outer solar system more feasible with each passing decade. The costs of space missions, while still high, have been decreasing in real terms as launch costs drop and spacecraft become more capable and efficient. The success of New Horizons demonstrated that fast flyby missions to distant objects are feasible and can produce spectacular scientific returns. Perhaps most importantly, public and scientific interest in the outer solar system remains strong, with each new discovery generating enthusiasm for further exploration. Private space companies might also play a role in future outer solar system exploration. Companies like SpaceX have expressed interest in missions beyond Earth orbit, and wealthy individuals passionate about space exploration might choose to fund missions to objects like Haumea. While private funding of deep space science missions remains speculative, the landscape of space exploration is changing rapidly, and pathways that seemed impossible a decade ago may become viable in the coming years. Until such a mission occurs, we continue studying Haumea from Earth using increasingly sophisticated techniques. Advances in telescope technology, particularly the development of extremely large telescopes with mirrors 30 or 40 meters in diameter, will provide better views of distant Kuiper Belt objects. Adaptive optics systems that compensate for atmospheric turbulence are becoming more capable, allowing ground-based telescopes to achieve resolution previously possible only from space. Space-based telescopes like the James Webb Space Telescope can observe in infrared wavelengths where Haumea's thermal emission is stronger, potentially revealing temperature variations across its surface that indicate different surface materials or geological features. New techniques for analyzing existing data also continue to yield discoveries. Machine learning algorithms can find patterns in data that humans might miss, potentially identifying subtle features or relationships that reveal new information about Haumea. Improvements in theoretical modeling allow astronomers to make more accurate predictions about Haumea's interior structure, ring dynamics, and orbital evolution, predictions that can then be tested against observations. The study of Haumea also benefits from the study of similar objects. As astronomers discover and characterize more Kuiper Belt objects, patterns emerge that inform our understanding of individual objects like Haumea. Comparative planetology, examining many worlds to identify common features and unique characteristics, is a powerful approach that has driven much progress in planetary science. Every new Kuiper Belt object studied adds to our collective knowledge base, and insights gained from one object often illuminate others. The cultural impact of Haumea, while not as significant as that of planets like Mars or Jupiter, or even Pluto, shouldn't be overlooked. For those who follow astronomy and space exploration, Haumea represents the cutting edge of discovery, an example of how scientific knowledge expands into new frontiers. It appears in popular science articles, astronomy podcasts, and educational materials, gradually entering public consciousness. Teachers use Haumea as an example when discussing the diversity of solar system objects or the physics of rotation. Science fiction authors might one day use Haumea as a setting for stories, imagining futures where humans or their robotic emissaries have reached even this distant outpost. The choice to name Haumea after a Hawaiian goddess has additional cultural significance. It represents recognition of Hawaiian culture in the international astronomical community and acknowledges the importance of Hawaiian locations, particularly Mauna Kea, in modern astronomy. Mauna Kea hosts numerous world-class telescopes that have contributed to countless discoveries, including observations of Kuiper Belt objects. However, the astronomical use of Mauna Kea has also been controversial, with some native Hawaiians objecting to the construction of telescopes on what they consider a sacred mountain. The use of Hawaiian names for celestial objects discovered using these telescopes thus carries complex cultural dimensions, representing both respect for Hawaiian culture and the ongoing tensions surrounding the use of Hawaiian land for astronomical research. These considerations remind us that science doesn't exist in a vacuum, but is embedded in social, cultural contexts. The story of Haumea includes not just the physics of its rotation and the chemistry of its surface, but also the human dimensions of who discovered it, where they discovered it from, what they chose to name it, and who cares about this knowledge and why. Science is ultimately a human endeavor, driven by human curiosity and shaped by human contexts. As we contemplate Haumea spinning through the darkness of the Kuiper Belt, we might reflect on what it means for us here on Earth. In one sense, it means nothing at all. Haumea has no effect on our daily lives, no influence on Earth's climate or geology, no resources we could exploit, even if we wanted to. It's simply there, existing regardless of whether we know about it or care about it. Yet in another sense, Haumea means everything. It represents our species' growing ability to understand the cosmos, to reach out with instruments and intellect across billions of kilometers and comprehend worlds utterly unlike our own. The same scientific methods, the same physics and mathematics that allow us to understand Haumea also allow us to understand Earth itself, to predict weather and climate, to comprehend plate tectonics and magnetic fields, to explore our own world's history and predict its future. The technologies developed for astronomy, from advanced optics to computer processing to data analysis techniques, find applications in medicine, communications, and countless other fields. The inspiration generated by astronomical discoveries motivates young people to pursue careers in science and engineering, ultimately contributing to technological progress that benefits everyone. Moreover, there's intrinsic value in knowledge and understanding. Humans are curious creatures who find meaning in comprehending the world around us. We tell stories, create art, write music, and conduct science, all as expressions of our drive to make sense of existence. Understanding Haumea doesn't solve practical problems, but it enriches us intellectually and spiritually, adding to the vast tapestry of human knowledge. Future generations will build on what we've learned, asking new questions we haven't thought of, making discoveries we can't imagine. The knowledge we're gathering about Haumea today becomes part of that foundation, a contribution to the long-term project of human understanding that extends across generations and centuries. There's also something profound about the mere fact that we can know about Haumea at all. Consider the chain of events required. The formation of the solar system 4.6 billion years ago, creating Haumea and countless other objects. The collision that transformed Haumea billions of years ago. The evolution of life on Earth over billions of years, eventually producing humans with complex brains capable of abstract thought. The development of human civilization with its cumulative technological progress. The invention of telescopes and computers and all the technologies needed to detect and study distant objects. The specific efforts of astronomers who chose to search for Kuiper Belt objects and who happened to observe the right patch of sky at the right time. All of this had to happen for us to know about Haumea's existence. From Haumea's perspective, if we can imagine such a thing, Earth is equally remote, a tiny blue-white dot lost in the glare of the sun. If some hypothetical inhabitants of Haumea possessed telescopes and turned them toward the inner solar system, they would struggle to detect Earth at all, let alone study its properties in detail. The fact that we've detected each other across this vast gulf, that we on Earth have come to know this distant spinning ice world, represents a triumph of human ingenuity and persistence. As our technology continues advancing over the coming decades and centuries, our knowledge of Haumea will undoubtedly grow. We'll refine our measurements of its size, shape, and rotation. We'll better understand its ring and may discover additional rings or moons. We'll characterize its surface composition in increasing detail and perhaps detect signs of geological processes we haven't yet recognized. Eventually, we may send spacecraft to visit Haumea, finally seeing this bizarre world up close and answering questions we can't address from Earth. Each advance will bring new insights and typically new mysteries, maintaining the cycle of discovery that characterizes scientific progress. The ultimate fate of Haumea, billions of years in the future, is interesting to contemplate. The dwarf planet will continue spinning through the Kuiper Belt, its rotation gradually slowing over immense timescales due to tidal interactions with its moons and the subtle effects of solar radiation. Eventually, perhaps in hundreds of billions of years, Haumea's rotation will slow enough that it no longer maintains its elongated shape, and gravity will pull it toward a more spherical form. But long before that happens, the Sun will have evolved through its red giant phase, expanding to engulf the inner planets before collapsing into a white dwarf. The outer solar system, including Haumea, will survive this transformation, finding itself orbiting a dim stellar remnant in a solar system devoid of living worlds. But these cosmic futures are so distant as to be almost meaningless from a human perspective. For now, in our brief moment of cosmic time, Haumea spins and we observe it, and that is enough. It exists as one of the most unusual worlds yet discovered, a testament to the incredible diversity of objects in our solar system and throughout the universe. Its rapid spin, elongated shape, ring system, moons, and collisional family make it scientifically valuable and inherently fascinating. Its distance and faintness make it challenging to study, driving technological innovation and requiring international cooperation. Its name honors Hawaiian culture while following astronomical naming traditions. Its discovery sparked controversy while advancing our knowledge. Haumea is all of these things simultaneously, a world that defies simple categorization and reveals new complexity with each observation. It reminds us that even in our own cosmic neighborhood, in a region of space humans have been observing for decades, extraordinary objects await discovery. It demonstrates that the universe is more creative and diverse than our theories predict, constantly presenting us with phenomena that challenge our understanding and force us to expand our models. It shows us that science is never finished, but rather is an ongoing process of discovery, refinement, and occasionally revolution. As this exploration of Haumea comes to its conclusion, we're left with a sense of wonder at this bizarre spinning world and appreciation for the scientists who discovered and studied it. Haumea may be far away, unreachable with current technology and invisible to the naked eye, but it's real and it's extraordinary. Somewhere in the darkness beyond Neptune, 6 billion kilometers from the warmth of the Sun, this elongated ice egg spins through the void, accompanied by its 2 moons and delicate ring, a cosmic oddity that enriches our understanding and reminds us that the universe is far stranger and more wonderful than we could ever imagine. And that, ultimately, is what makes Haumea worth knowing about, worth studying, worth celebrating as one of the most unusual planets in the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.